For today's video, we're going to talk about breadboarding. So you guys have some basic knowledge of electrical circuits. We know how to set them up and to draw them. So now we're going to build them, and to build them, we're going to use breadboards. And breadboards are an easy way for us to make small circuits. So this is what a breadboard looks like. They're really useful for prototyping, and we can reuse them. The holes are for sticking wires in, and these breadboards are a little intimidating at first. They look like they're super complicated and they're hard to learn, but they're really not. They're not that bad. So we're going to go over the basics and figure out how to use these. So why would we want to use a breadboard? It can be a quick and cheap way to make a circuit. So it lowers the fabricating costs. Because of the cost, the breadboards are reserved for the final working design, and then, the printed circuit boards are just for the final working design. And then this is an easy way to simulate how circuits are going to work. So let's get to how they work. So all of the vertical columns on the outer portions are connected together, and you'll see there's a positive and a negative, and so those are locations for us to attach power outlets. So the positive end of the battery or power outlet, and the negative end of the battery. The horizontal rows are connected to each other. So letters A, B, C, D, and E are all connected. So there's basically a wire connecting all four of those spots. It is not connected to the other side, but letters F through J are connected to each other. So you could plug something into A and plug something out of C, and it would be like connecting a wire to each end. So F through J are connected. The holes that we see are places for us to insert wires. We have limited supplies, so we may not do this as much as the Project Lead the Way suggests. So they suggest a good circuit board uses really tight wires. You can see here that there's way too much wire on these, but this involves cutting the wires to a very specific size, and we have a limited amount of wire to use, so we may not always do this. But the first part about using as few jumpers as possible, so jumper is a wire that connects one location to another. We want to use as few as possible. That is something that we'll try to do. But we don't have to necessarily cut the wire unless it's a ridiculous size. Like this green one is pretty long. We could probably come up with something a lot smaller. So some general tips for getting started anyway. We're going to be using circuits that we've already looked at before, so either ones that we have drawn or ones that we've made using the FET simulation. So when we start circuit boarding, we're going to try to make the circuit as close to our schematic that we made as possible. So if you get lost, you've got an easy way to refer. So using this schematic, and check off the components and wires as you add them. Again, we may cut or not cut as much as they want us to. So it says cut component leads to short lengths to avoid contact and shorts. That part is referring to the metal end. So the metal part that's not insulated, that does need to be as short as possible, because if this is an exposed wire, then that'll make some short circuits. So these weren't covered with insulation, we'd probably have a short right here. So we do want to keep the metal exposed part as short as possible. And then have somebody else check. So if you get stuck, have your partner check before you call your teacher over. We're going to be using diodes. Diodes are light bulbs, but diodes only allow current to flow one way. So Electricity goes from the negative to the positive, so the shorter wire is the negative, and then if the wires for some reason get cut, or maybe they got bent and it's hard to tell which one's the longer one, there's a large metal component inside the light bulb, and the large metal component has flat spots on the negative end. We're going to be using resistors. The rest of this PowerPoint is dedicated to talking about how we know what resistance a resistor has, so what those bands mean. So the squiggly line is our symbol for a resistor, and this resists the flow of electricity, which we already know, and the more it resists the flow of electricity, the bigger the resistor. And it's represented with an ohm, or this upside down horseshoe. So there's different types of resistors. There's the kind that we'll be using that look like these with 4 bands on them. There's carbon film resistors that have 5 bands. There's variable resistors that change the amount of resistance that they have. So if you have a dimmer switch on a light at home, that uses something called a potentiometer, and potentiometers change the amount of resistance that go through them. So you can change it to a high amount of resistance, which makes the lights go dim, or a low amount of resistance, which makes the lights go up. And then a surface mount resistor, which I honestly don't know what it is, so we'll just skip that one for now. So for our color-coded resistors that we're going to use, there are 4 bands, and each of the bands represents a different number in our resistor. And we can use a multimeter to measure it, so we will be getting these out at some point. And anytime you want to measure the resistance of the resistor, you need to detach it from the breadboard, hook it up to the multimeter, and then the multimeter will use its own battery to run electricity through the resistor to measure its resistance. So this is how we read the bands on a resistor. The first band represents the first digit. The second band is the second digit, and then the third band is the multiplier. So depending on what it is, excuse me, we could multiply the sum of these two to get our actual value. And then the last one is not super important to us. It's the tolerance, so it's how accurate the resistor is made. So it could be not very tolerant or pretty tolerant. So if you have a sensitive piece of equipment, then you would want a high tolerance on your resistor. So for us, we're probably for the most part going to ignore this last band. We're just focused on the first 3. So here's an example. So let's determine the resistor value of what we have here. So we've got our first band is brown, which is a 1 digit. The second one is black, which is a 0 digit, and then we have a multiplier of red, which is 100, and then for now we're just going to ignore the tolerance. So we have 10 as our number, so we add the first 2 bands together. So we have our first digit is 1, second digit is 0, so that's 10. We have a multiplier of 100, so 10 times 100 is 1,000. So the total resistance of this resistor is 1,000, and that's with a tolerance of plus or minus 5%. Here's example number 2. So we have orange, white, and green. So orange is 3, white is 9, green is 100,000. So 39 times 100,000 is, let's see, is that 3.9 million? So it's 3.9 million ohms. And our last example, so we need to determine the color bands that would be on a 1.5K resistor band. So first digit is going to be a 1, so that should be a brown. Second digit is a 5, so that should be a green. And then we need that to be multiplied by so it'd be 15 times 100, right, to get 15,000. So the multiplier is going to be 100, which will be red, and the tolerance is 5%. So we're going to have a gold band for the last one. So here's the answer down here. So it's brown, green, and then that's supposed to be red. It looks like they have an orange there, and then gold for the last one. And anytime we want to measure the resistance of something, we're going to unplug it from the circuit and then hook the thing that has the resistance up to a multimeter. And then someday, very soon, we'll talk about how to use a multimeter. And that concludes this video.